In this video, we're going to outline a proof of the fundamental theorem of calculus part 1. So what we're going to do is we're going to look at the area so far function, a of x, and it is calculating the area under the curve f. Y is f of t. We just need another letter than x, right? It's calculating the area under that curve bounded by the vertical lines, x is a, and x is wherever we tell it to stop, right? And we're finding that area. This is a function of x, not t. Where in the domain do you want to stop that integral? Where in the domain do you want to cut off to find the area under the curve? Cut off, find the area under the curve. Okay, so let's go ahead and look at these in terms of area. So this first picture, that blue area, if I write that as an integral, that's the area under the curve f bounded by the vertical lines, right? X is a, and stopping right here. Where'd we stop? At x plus h. X plus a little bit. That's the blue area. In function notation, it's a of x plus h, right? When we put in x plus h into the a box, where do we stop our integration? At x plus h. If I replace x with x plus h, this is what we have. Now this area, the area under the curve f as x goes from a to x, that is area under f as x goes from a to x. From a to x, where you cut it off. In the area so far function notation, that's just a of x, right there, that green area. I think I'm going to erase these orange and yellow lines. They're a little distracting. Green area. Right? Here's our blue area. Here's our green area. Now here, this pink area is the area under the curve f going from x to x plus h. X to x plus h, area under f. That's exactly what that pink area is. But for a very, 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 very small h, if h is tiny, this rectangle right here is super, super close to the pink area. It's almost the same. For a very, very small h, they are essentially the same. Okay? What is the height of this rectangle? It's f of x. And the base of this rectangle is h. So the purple area, which I drew again right here, how about we shade it? This purple area right here is very, very, very close to the pink area. And the pink area is the blue area, take away the green area, right? If I chop off the green, I've got the pink remaining. So blue minus green is very, very close to purple area. And that's exactly what we have written right here. Just made it a little bit smaller. Blue minus green is exactly pink, and pink is almost purple, right? And that's what's written right here in our function notation with that area so far function. Blue minus green is really, really, really close to h. If I divide both sides by h, which I can do because h is not 0, we're taking h to be a very, very, very small positive number, and then take the limit of both sides, this left-hand limit should look very familiar. I want you to pause the video and think about what that's the limit of. It's the limit of rise over run as run goes to 0. On what function? The a function, the area so far function. So that is just a prime of x. And the limit as h goes to 0 of f of x is just f of x, because f of x is constant with respect to h. There's no h's there. F is constant. I'm going to write WRT, but for with respect to h. So here's the big conclusion. The derivative of the area so far function is my height function. When we differentiate a, we get f. In other words, that is a. What's a again? The integral from little a to x of f of t dt is an antiderivative of f of x. Right? What does it mean to be an antiderivative? It means that when you, looking for a color, when you take the derivative of a, you get f. So a is an antiderivative of f, right? And that's exactly what we have written right here. The derivative of a, here I'm using my derivative operator notation. What's a? A is typed right here. A is a function of x, is just f of x. That is what we're saying is the rate at which the area is changing is my height function, which is somewhat intuitive. For a very, 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 we're drawing the h huge, but for a very, very, very small h, you're adding on a little teeny amount of area that is our height function. That's the rate at which that area is changing. Said another way, for continuous functions, differentiation and integration do and undo each other. That is, integration is anti-differentiation. Here we have our fundamental theorem of calculus typed up nice to us. If we have a continuous function on a closed bounded interval, then this area so far function, it's continuous, it's differentiable. And this is the big one. When you take the derivative of it, you get that height function. Now I encourage you to go ahead and actually read the formal proof if you want for the fundamental theorem of calculus part 1. Right here, continuous function on a closed bounded interval, you must have an absolute max and an absolute min on that interval. In our previous lesson, we talked about properties of integrals, and right here you're going to be able to squeeze your integral knowing that there's an absolute max height and min height using this property. And then back with our limits at the beginning of the class, using the squeeze theorem, this delightful result will pop out. So I encourage you to go ahead and do that, just because math is a rigorous language, it's very logical, and it's fun to go back and remember previous theorems and apply them. But for right now, here's the big upshot. Just like addition and subtraction do and undo each other, much like multiplication and division do and undo each other, differentiation and integration do and undo each other. There's a beautiful relationship between our tangent question and our area question. Thank you for watching.